Okay, so yesterday we were talking about the heating curve of water. We talked about how as you add heat to any material, okay, either its kinetic thermal energy is going to change, which means its temperature is going to change, or its potential thermal energy is going to change, which means it's going to change state. Okay, either it's going to melt or freeze, okay, or it's going to vaporize or condense. Okay, one or the other. So that's what we were talking about, and then we looked at what formulas we would use on the different parts of the graph, and that's where we finished off yesterday, okay, talking about what parts of the graph involve a change in kinetic energy and thus use E equals mc delta T, and which parts use E equals mLF or MLV, okay, because they're changing the potential thermal energy. So what we arrived at yesterday was anywhere where the line is going up, okay, the temperature is changing, and thus the kinetic energy, kinetic thermal energy, is changing, and for any of those places, we would use E equals mc delta T. Okay? If we are going from a solid to a liquid, okay, or a liquid to a solid, you can go backwards, all right? The amount of energy would be calculated using E equals m times LF, where m is still the mass in grams, and LF is the latent heat of fusion. For water, which is the only substance we're going to do, that number is 333 joules per gram. Okay, we talked about how the snowball makes your hands cold. And then the other state change, okay, is right here, okay, and that involves taking a liquid to a gas. It involves the most energy of any part, okay, in this entire sequence, and for that part, okay, we would use E equals MLV, and I had you guys either take a picture of that diagram yesterday or draw it yourself or whatever. Okay, so M is again the mass in grams, and LV is the latent heat of vaporization for water, 2,260 joules per gram, and that's where we ended off. We were talking about why, you know, when you walk through the mister at the Stampede, you feel cooler because it takes all that energy to evaporate the water that lands on you. Okay, everyone with me there? Ringing a bell? Okay, so here's the next step. All right, I want to be able to calculate how much energy is involved in taking water from one temperature to water at another temperature. Okay, and I don't mean like it's only a liquid. I mean it could be ice at some minus something and going to steam at something. Okay, I think at the end of the day yesterday we were looking at having a block of ice going from minus 25 to steam at 150. Okay, so we are going to do a sample calculation of that. All right, so can you guys copy that down? And then we're going to walk through the steps. The steps are really easy. There isn't even any algebra. You just have to plug numbers into the formula, right? But we need to kind of know what the steps are. Okay, so get that one written down and then write down what I do as I go through it. Okay, so now we have that. Okay, what do I do with all of those numbers? Add them all up. Yeah, I'm looking for the total amount of energy. Step one, okay, required 7,935. Okay, so and plus that, plus that one, plus that one, plus that one. Okay, so the total amount of energy to take a 250 gram block of ice, so 1 cup of ice, okay, and heat it from ice at minus 15 to steam at 150 is going to take 786,435 joules. Okay, now, I would not give you a 5-step problem on a unit exam. It takes too long, okay? I can test whether you know how to do this with a 3-step problem. And I will test it with a 3-step problem. All right, so it would probably be something like this. You have a block of ice at -10 and you want to heat it into water at 45 degrees. Okay, so I'd have to heat the ice, melt the ice, heat the water. Done, 3 steps. Okay, or you have liquid water at 80 degrees Celsius and you want it to be steam at 120. So I have to heat the water to 100, I have to boil off the water, I have to heat the steam, 3 steps, I'm done. Okay, everyone kind of follow what I'm looking for there? Okay, but the idea, the method is still the same. You draw the heating curve of water, okay, like we did here. You mark the starting point and the ending point, and you figure out everywhere where the line changes direction is the end of one step and the start of the next. Okay, then figure out what formulas you need for each step, plug in the numbers and solve. Okay, so method is always the same. We're going to go through a bunch today, so if you didn't kind of follow the first one, okay, or you were watching this and I didn't record it, so you missed it all, okay, we'll do some more. Okay, now a 5-step question would be 12 marks. Okay, because I would give you a mark for this, and I would give you 2 marks for each step. Okay, that would be identifying the correct formula and getting the right number, okay, for each step, and then 1 mark for your final number. Okay. So, for a 3-step question, it would be at 8 marks. Are they 8 pretty easy marks? Like, you don't have to manipulate anything, you just have to plug numbers in and add them all up. Okay, so it shouldn't be too mathematically challenging for you. Okay, so what I would like you guys to try right now is question number 1. This would be exactly like what I would give you on a unit exam. Okay, so try question number 1. I'll give you a few minutes on that one, and then we'll go through it together. Okay, then we'll look at the other questions on the previous page. So, first thing we want to do is just draw like a miniature version of that heating curve of water. Okay, we're starting with water at 3 degrees Celsius. So that means we're starting about there, and we're going to steam at 115. So we're going to there. How many steps is that? How many? 3. 3 steps. I have to heat the water to boiling, boil off the water, heat the steam. Okay, those are the 3 steps. So, what we have to remember then is what happens at each step. Okay, so in step 1, I'm actually changing the temperature of liquid water, which would mean I would be using this formula, E equals mc delta T. Okay, in step 2, right, I'm going to be boiling off all of that water. In order to calculate how much energy is required to vaporize something, I use that formula, E equals mLV. That's the only thing you have to memorize here, okay, is what formula to use where, right? And then in step 3, I'm changing the temperature of the steam, so we're back to E equals mc delta T because the temperature is changing again. Right? Everybody with me so far? Okay, so when we're plugging in our numbers here, we know the mass is 400 grams. Okay, so for step 1, we're looking at 400 grams times 4.2, which is the specific heat capacity of liquid water. Okay, and I'm changing it from 3 degrees to 100 degrees. So what's my temperature change? 97 degrees. Okay, so 400 times 4.2 times 97. All right, so we're looking at 162,960 joules. All right, then in step 2, I would still have 400 grams, and now I'm vaporizing it, so I got to multiply by LV, which is 2,260 joules per gram. Okay, so 400 times 2260. So that's going to take 904,000 joules. Okay, and then I have to heat the steam up. So still 400 grams, but now it's steam, so I have a different heat capacity, 2.02, and I'm heating it from 100 to 115, which is 15 degrees. Okay, so we're looking at 12,120 joules. Okay, what would I do with those three numbers? Add them up, right? Okay. We're looking for the total amount, so plus that number, plus that number. Okay, so we're looking at 1,079,080 joules. Okay, everybody all right with that one? Okay. All right, so they all work pretty much the same. Okay. All right, what I would like you guys to do right now, eventually when the screen changes, here we go. Okay, is I would like you to work on these questions here. Okay, so like writing down an explanation answer for 1, 2, and 3. Okay, and then I'm not going to do 4 or 5 or 6, but we'll start on 7. Okay, so we'll do 1, 2, and 3. I'll give you a few minutes to get some explanation answers written down for 1, 2, and 3. Then we'll work on 7, and that's what we're going to work on today, is just making sure we understand how these problems work, because there's a 3-step problem worth 8 marks on your unit exam. Okay. All right, so we kind of talked about these a little bit here, but if you put ice cubes into a drink, okay, they keep it cold because of the law of conservation of energy. Okay, as the drink tries to warm up, okay, the energy from the drink goes to the ice cubes because they're essentially a heat sink. Right? They're going to absorb energy because they have less total thermal energy than the water does. Right? They are actually going to be at around the same temperature as the water, but the energy is still going to flow into the ice cubes because they have less total thermal energy because they're still in a solid state. So the energy goes into the ice cubes and the ice cubes melt. Okay? That results in basically keeping the drink's temperature around the same temperature as the ice cubes, okay, until the ice cubes are gone, at which point obviously their ability to absorb energy is also gone. Your drink is somewhat diluted and it will start to gain energy and increase in temperature from there. Okay? And sweat works in a similar way. If you start to sweat, okay, you get that thin layer of perspiration on your skin, and there's a breeze or you're moving, some of that water will evaporate, and it'll take 2,260 joules for every gram of it, most of it coming from your body, okay, which is going to cool you off. Okay? Now, from a genetics perspective, is it better to sweat a lot or a little? Which would cool you better? Because I mean, like, people sweat differently, right? Some people, they perspire. They get like little tiny beads of sweat, and that's like it, okay? And other people, they drip or gush sometimes, okay? Is it better to sweat more? Is it going to cool you better?
Yeah.
Actually, it won't. Because where does the sweat go? If you just sweat a whole bunch and you're literally dripping, where does that sweat go?
Drips off.
It drips off of you. Okay? If the sweat doesn't stay on your body, it's not going to take energy from your body to evaporate it. Okay? You're better off to have a thin layer of perspiration on your skin, okay, and not be just dripping wet, okay, in order to cool yourself off. Losing water, okay, to just having it drop off of you doesn't help at all. All right? Back probably about now like 10 years ago or so, the Edmonton Oilers had a goaltender named Nikolai Habibulin. Okay? This guy, like, he would lose 10 pounds in a single game because he would sweat that much. Okay, like this guy, every time there was a stoppage in play, would skate to the bench to get a new blocker and a new catcher because they would be soaked. Okay, the guy just sweat like crazy, and at the same time, you get like 2 new water bottles and go back to the crease. And they actually caught on the crease cam one time water, sweat, dripping out of his skates because he had drilled holes in his skates to drain the sweat. Otherwise, his skates would fill with what? With sweat. This guy, like, he was a puddle. Okay? That's why the Oilers couldn't win in a shootout, because by the time they got to a shootout, the guy had lost 10 pounds and he was cramping up and dehydrated. Okay? So it didn't really help cool him off. He just one of those guys that pours sweat. Okay? And so lost a lot. It didn't make him any cooler than anybody else. Okay? It just means that he sweats a lot. Okay? So being a big sweater doesn't really mean that you cool your body any better than someone who just perspires. All right, why would gardeners spray their crops before a frost? So you get a thin layer of water on the leaves of a crop, okay, and then the temperature drops below freezing. Why will that protect your crop?
Because when the water on the plant starts to freeze, it releases heat.
Exactly. When the water that's on the surface of the leaves freezes, it releases sensible heat, okay? Because now it's changing from liquid to solid, right? That's actually going to protect and keep from freezing the tissue of the plant that it's on, right? Now, that only works if it's a light freeze. If it's gonna drop down to like -6 or 7, your plants are toast anyway, okay? But if it's just gonna be a light freeze, it can work. They often do this with like fruit trees in places that might experience light frosts. Okay, golf courses will do it with their greens in order to protect the bent grass that's on the greens from frost. Okay, so they'll actually just water the greens, just douse them down real good, and then that water might freeze, but the grass itself will not. All right, how many people are done number 7? Okay, I'm gonna give you a bit of time to do number 7. If you're done number 7, you can try number 8. I'll go through number 7 in like another 5-10 minutes. Okay. Actually, let's just start number 7 together. Okay, so I draw my heating curve for number 7. I want to melt 0.1 kilograms, that's 100 grams, okay, of ice initially at -20. That's where I want to go. I want it melted. I want the water to have a temperature of 0 degrees Celsius. How many steps? 2. Okay, just 2 steps. Okay, so for number 7, we said we have 2 steps. Okay, in step 1, I'm heating up ice. Okay, and I'm heating it by 20 degrees Celsius. So that's meaning I'm going to use MC delta T. Okay, the mass is 100 grams. Since it's ice, the specific heat capacity is 2.116 joules per gram degree Celsius, and I'm heating it by 20 degrees Celsius. All right, so we're looking at 4,232 joules. Okay, our second step is we have to melt the ice. Okay, so for melting the ice, the formula for melting is E equals mLF. Okay, the latent heat of fusion, freezing and melting. Okay, and so then we would have our 100 grams times LF, which is 333. Okay, so 100 times 333 plus our previous answer. All right, so we're looking at 37,532. Okay, everybody all right with that? Okay, all right. Try number 8. Also very similar to one you might get on a unit exam. Okay, so give you guys a few minutes to get ahead of me on that one, and then I'll do the steps, and then I'll give you a few more minutes. Okay, let's just look at how many steps this one is. Okay, so we draw our heating curve, okay, and it says we're starting with 0.05 kilograms, that's 50 grams, okay, of ice initially at -10, so there, going to water at 80, that's there. How many steps? 3. Okay, we've got to warm the ice to melting, we have to melt the ice, we have to heat the water, 3 steps. All right, so step 1, we're heating up the ice. All right, so that's going to be E equals M times C times delta T. So that'll be our 50 grams times 2.116, the specific heat capacity of ice, times 10 degrees Celsius. That's the amount we're changing the temperature by. All right, oh, not times 1, times 10. So that should be 1,058. 1,058. Okay, joules. And then for step 2, we're melting the ice. Okay, whenever we're melting something, we use E equals MLF. Okay, so that's going to be 50 grams again times LF, which is always 333. Okay. All right, so that's going to be 16,650 joules. And then for step 4, we have to heat the water. Okay, anywhere where we're heating something and changing its temperature, we use E equals MC delta T. Okay, again, it's 50 grams. Now it's liquid water, so it's 4.2. And we're going from 0 to 80. So that's 80 degrees. All right, so that's 16,800 joules. Okay, then when we add those 3 numbers together, we should get 34,508 joules. Okay, everybody all right with that? Okay, that's a very typical exam level question. Okay, while I'm thinking about it, couple of reminders, okay? Overdue assignment deadline. So if you have any assignments that you have not handed in and you would like them graded, okay, and put into your marks before your final exam, I must have them January 18th at 3:20 p.m. I will not accept anything for grading after that. I want you to be able to come here on the 19th and know exactly what you're going into the final exam with. Okay? So make sure you have them to me by then. I will not be looking at Google Classroom again after that point. Okay, so they must be handed in then. Okay, don't come to me the day after the exam and go, hey, Mr. Codere, look, I did all these things. And I'll be like, my grades are done. Okay, so make sure you have it in to me by that time if you want it marked. Okay. Also, reminders that obviously the Unit 4 exam, okay, for this unit, which we're going to do a review for tomorrow, okay, is going to be on Tuesday, January 17th. And your final exam, January 25th, 9 o'clock a.m. in St. Vincent de Paul, which is down the math wing. Okay, so that is where that exam will be, okay, at that time. Questions on that? Okay. So I would like you to just work on a few of these problems. They are in your digital workbook and they are on page 4. Okay, and there's some additional ones on page 5. There's another 5 there. Okay, so these are the ones we've been doing. Okay, we just did number 7. So okay, you can work on these ones here for the remainder of the class. Okay, if it's something you need help with, pop in and see me. And I can give you a hand with it. Oh, and also guys, I believe I posted yesterday in the stream the review package. So if you were wanting to have a look at that before tomorrow's review, that might not be a bad idea. And then you know maybe what questions you need to ask and things like that, but it was posted yesterday. So you can have a look at that as well.